Hi, welcome to the International Space Station Flight Control Room. We are here for a distance or digital learning network event, and we're talking with the middle school kids at Lanier Middle School in Buford, Georgia. So today we have a special guest for you guys because I understand you guys have been studying about Earth and Earth science, and it's a good time because this is Earth Month here at NASA. So here with us today we have Will Stefanov. He is the Chief Earth Scientist here at the NASA Johnson Space Center. Welcome, Will, and thank you for coming.
Hi, thanks, Mikko.
Thank you. So guys, we're ready to take your questions.
Leah, go ahead for the first question. How can you see the difference between the past and the future and the present? And what shows the plate tectonics in the satellites?
That's an excellent question. Sorry, I have to get myself arranged here. That's an excellent question. The way that you look at changes in time with satellite data is you collect lots and lots of images over a long period of time. A good example of this is the Landsat satellite series, which has been collecting data since 1972. So when you have all these scenes, you can line them up and just look at them directly to see what's changed over time. Like you can see things like change in vegetation, growth of cities, new lava flows from erupting volcanoes, things like that. For the plate tectonic question, it's hard to actually measure or see plate tectonics from satellites, but what you can see is the effects of plate tectonics. So you can see where volcanoes are erupting, because volcanoes are typically associated with plate tectonic activities. You can see damage from earthquakes, and for some different kinds of satellite sensors, like GPS satellites, we can actually use that information to measure the height of mountains and how they're growing over time, so we can see how that part of the plate tectonic process is working as well.
That was a good, smart question. Do we have another one?
Next one. How are satellites kept from damage?
Also a very good question. Satellites typically, unfortunately, they don't have shields like you'd see in Star Trek or something like that. Most satellites, the best way to protect them is by putting them into orbits high enough so that they're out of most of the orbital debris that blankets, well, that doesn't blanket our planet, but orbits our planet. The orbital debris itself is caused by old satellites, pieces of old satellites, pieces of old rocket launches, as well as natural debris like meteors that enter the Earth's atmosphere all the time. So there's groups both here at NASA and in the Department of Defense that actively track about 500,000 little objects, some smaller than the size of a baseball, and they track these every day as they orbit around the Earth. And the whole purpose of that is so that they can warn manned spacecraft like the International Space Station when orbital debris might be approaching them, so they can maneuver the station out of the way. For satellites that aren't manned, typically, like I said, they put them into high orbits so they're out of the path of most of this orbital debris. But satellites do occasionally get hit by things, and sometimes they get hit by other satellites, which has happened over the past 10 years a couple times.
Good question.
How long does it take to process information from satellites, and what kind of information can you get from them?
That's a $20,000 question. The time with satellites that are up there now, the most recent generations of satellites, and the fact that you can put ground stations almost anywhere now to receive data from those satellites. Depending on the sensor, you can get data back in a few hours and have it available for either scientists or the public to look at. The things you can measure from satellites is, I won't say it's endless, but pretty much almost anything about the surface of the Earth and the atmosphere you can measure from a satellite. You can look at things like surface compositions of different materials, like the elements or the minerals that make it up. You can look at the composition of the atmosphere or the presence of pollutants in the atmosphere. You can look at things like surface temperature, like the surface of the land surface temperature or the ocean surface temperature. You can look at things like vegetation extent and health over the entire globe. It's really, the possibilities are really defined by the physics of the electromagnetic spectrum.
Very good question and very good answer. Do we have another one?
What is one of the satellites that take the best and most up-to-date photos?
That I'd have to say is in the commercial satellite realm. There's a number of commercial satellites that collect data of fine enough resolution or surface detail that you can see things that are less than about 1.5 feet apart on the ground from orbit. And one of those satellites is called GOI. In fact, some of the imagery, if you look at Google Earth, some of the imagery that you see in there, when you can zoom down to the street level, not the street level itself, but just above the street level, that's from satellites like this, that kind of resolution. In fact, some of them collect data that's so finely detailed that you can't release it to the public because it's a security concern. But other satellites, other sensors are designed so that they collect more information over the same spot on the Earth in shorter timescales. So some sensors can take data several times a day over the same spot on the Earth, as opposed to getting really high resolution data. It's kind of a trade-off right now. Our technology is still at the level where you either get really, really detailed information, or you get a lot of information over the same spot, but you don't typically get it at the same time.
Very interesting. I can tell you guys have done your homework. We got another question?
How long will it be until the next Pangea or supercontinent forms?
That's an excellent geological question, right close to my heart. The supercontinent Pangea, the last one, we think there's been 6 in geological history. The last one formed about 300 million years ago and then started to break up about 200 million years ago. And we can look at the way the plates are currently moving today and make predictive models of, if everything continues the same, what will happen. So the current predictions are that we might see another Pangea-like continent, which geologists are calling Pangea Ultima, in about another 250 million years or so.
How long do you have to be in college before you get to work at NASA as a NASA scientist?
That's an excellent question. The answer is it really kind of depends on what you want to do in NASA. There's a wide range of job opportunities available. You can be, I would have to say that probably getting a bachelor's degree is the basic minimum that you might want to do, so 4 to 5 years in college. But you could be a computer programmer, you can be a scientist, you can be an engineer, you can be a writer, you can be a speaker, you can be a TV producer. It's all really depends on what you want to do. But I'd say a bachelor's degree is probably the minimum. For some things, you might need a more advanced degree, like a master's degree or a PhD, and that adds more years to your time in school.
But it starts where you are now.
Exactly.
Every course you take, every year that you add more education to yourself is something that only enhances your knowledge and will pave the way to where you want to go. So keep studying.
Exactly right. Yes.
We have another question?
Is there a chance that one of our current continents will split again? If so, which one would be most likely to split?
Well, okay. I think you're asking if we're going to see any large new separations of continents. Probably not. As I said earlier, the current thinking is that we're actually entering a phase where the continents are starting to come back together again over the next 250 million years or so. That being said, there is an active rift, an active area where there is a little bit of continental splitting going on right now in East Africa, the East African Rift. And that's where basaltic magma is coming up through the Earth's crust and actually splitting off the Horn of Africa, the easternmost part of Africa, away from the rest of the mainland. So that's going on right now. But apart from that, that's really about the only place where we're seeing a large-scale continental rifting going on.
Good questions.
If the ocean floor was a different rock than basalt, what would change about Earth?
Great questions for you, being a geologist.
That is a deep question. What would happen? The big answer is plate tectonics probably wouldn't work. At least it certainly wouldn't work the way we see it now, because the big difference between the oceanic crust and the continental crust is their densities. Continental crust is much less dense and light, so it has a tendency to sort of float. or raise higher on the Earth's surface. Oceanic basalt is very dense, so very heavy, and it's produced by magma from the Earth's mantle coming out and erupting along mid-ocean ridges. What that does is it creates new seafloor and pushes the continents apart. And that's one of the big driving factors behind plate tectonics. If it was all the same kind of material, then it would be very difficult to move them apart that way. Also, the heavy oceanic crust is recycled easier back into the mantle along subduction zones. And again, if the material was the same, it had the same density, that would be very difficult to do. So you wouldn't have this whole recycling going on. So that would be the major change. What that would mean to the way the Earth's surface would look, well, over time, you wouldn't have new mountains being formed, for one thing. And so you could expect that over millions of years, you might see the mountains starting to be eroded down to flat plains. That doesn't happen on Earth because we have active plate tectonics. That would be one major change, and of course that would cause a whole series of climatic differences, and a lot of stuff would be very different. So, very excellent question. There's a lot contained in that question.
Deep, literally and figuratively. Great question. Do we have another one?
How do you predict natural disasters?
Wow, you guys are just coming up with awesome questions. We can't really predict natural disasters with any degree of certainty today, but there are a lot of types of disasters that frequently give us warnings that something might be happening. For instance, large storm systems like hurricanes, we're now pretty good at being able to detect when those storms are forming and be able to detect where they're going to go. Maybe not so good on how strong they're going to be, but at least we can plot their tracks enough to let people know that a storm is coming so they can evacuate and get out of the way. For other things like volcanoes, volcanic eruptions, sometimes we can detect some of them sometimes. Occasionally volcanoes will have hot spots that you can detect from satellites in orbit that indicate that there might be magma coming to the surface and an eruption might be imminent. Also, sometimes the volcano shape itself changes as magma comes into the volcano and it causes the ground to raise. We can measure that with GPS sensors. Things like earthquakes, those are really difficult because earthquakes quite frequently occur with no advance warning whatsoever. Sometimes we know where earthquakes have occurred, so we can assume, based on the last time a big earthquake occurred, we can make some idea of when the next one might happen, but it's really just a prediction. It's really hard to predict to make a real certain deduction of when a big earthquake might occur.
How will the technology of the GOESR series satellites improve compared to the current GOES satellites?
It's an excellent technical question. The big difference there between GOESR and the current GOES satellites is in the sensitivity of the sensors and their capabilities. The GOESR satellite will still view the Western Hemisphere and will collect the same measurements that the current GOES satellites collect, but it'll have better imaging capabilities. It'll be sensitive to some new pieces of information that the current satellites aren't. And on the solar end, it's kind of the same story. Better imagers, better detectors for some of the solar particles that come back. And all of this is designed to give us better weather forecasting predictive capabilities.
Is it possible for a superstorm or multiple natural disasters at once to occur and cause mass extinction on the planet Earth?
This is another great question. I'd have to say the answer is probably no. And the reason I say that is because there's enough spots on the Earth that are geologically quiet. They're not prone to big earthquakes. They don't have active volcanoes going on, to where even if all the other ones went off, it wouldn't cause mass extinction of the human race. There would still be people left in those areas. What would be more likely to cause mass extinction would probably be something similar to what caused the dinosaurs' extinction, like a large asteroid impact on the surface. You'd need an event of that kind of magnitude to create enough environmental disturbance to really make the environment so inhospitable that we'd be looking at a mass extinction. But that's a great question.
Excellent.
At any point in time, will any landforms erode to a point that there isn't enough room for the organisms inhabiting it to remain stationary? If so, will they evolve into some other sort of life or migrate?
That's another great plate tectonic question. It kind of gets back to an answer to a previous question about what would happen if plate tectonics stopped working. That's really what you'd need to have happen to cause what you're talking about. There's actually a term that geologists use for that. Geologists about 100 years ago thought this same question. They said, "Why? How come we have mountains?" This is before plate tectonics was understood, and they were asking why don't the mountains just wear down to flat plains? We know now it's because new mountains are formed due to plate tectonics. But if that didn't exist, and you just had erosion, yeah, eventually you'd wear everything down to a flat plain. Now this wouldn't happen instantaneously. Of course, this would take hundreds of millions of years. So that's plenty of time for existing creatures to migrate, to adapt to new conditions, and so forth. So I think you would see adaptation occurring if plate tectonics stopped functioning. But things wouldn't go completely extinct.
Getting some zingers. These are good.
So I know that the plates they are shifting. So in the anywhere like in the next million years, would there be anything coming off of North America?
Whoops, sorry. The answer to that probably the short answer is no, except for probably Southern California. Most of the plate tectonic models show that Southern California over the next 50 million years or so is likely to break kind of along the San Andreas Fault and start moving towards Alaska. So California may get smaller, but that's about it.
Are the teachers who train astronauts actual astronauts themselves, or are they just people who use information from other astronauts to teach?
That's a good question. I'm actually one of the people who trains astronauts through the Crew Earth Obs project here. Astronauts, they do train each other in some aspects, but for science training, they're trained by people like me and others of my colleagues, other Earth scientists, atmospheric scientists. And for other technical issues, like for taking photographs on the ISS, they're trained by another group that is composed of expert photographers. So I guess the answer to your question is yes and no. For some things, the astronauts do train themselves, but for other things, they rely on outside experts.
Very good question. I think we actually have a website. Maybe we can get that for you guys when up here, just where you can actually go and look at a lot of those photographs that are taken from.
Yeah, absolutely. It's if you do a Google search on astronaut photography of Earth, it'll take you to the website. Yeah, and there it is.
Yep.
Does the upper atmospheric research satellite really have pieces falling on Earth, and wouldn't it burn up in the Earth's atmosphere?
That's an excellent question to ask because, as I said earlier, there's orbital debris and meteors falling on the Earth all the time, every day. Most of that stuff is so small that it does burn up in the atmosphere and it never hits the surface. For the UARS satellite, that was a little different case. That thing was the size of a bus. And when it entered the atmosphere, most of it did indeed burn up, but it was so big that some pieces did survive to go through the atmosphere. Now, most of those pieces fell into the ocean because the ocean covers 70% of the Earth's surface. And this happens to most stuff that actually makes it through the atmosphere to hit the surface of the Earth. There's been no reports that I know of, at least, of anyone being hit by any kind of debris from space, and certainly nothing from the UARS satellite.
How long does it take for information to be received from the satellite? Is there any delay, or does it happen in real time?
That's an excellent question. For most satellites, there is a slight delay time. Like I said earlier, if you have a receiving station, you can collect data from the satellite as soon as it passes overhead. But typically that data is in what we call raw. It's raw form. It needs to be processed before it can be usable by a scientist or a member of the public. So there typically is a delay time of a few hours before you get data from the satellite to the point where it can be distributed for use by other people. There are some other kinds of sensors, like on the ISS, there are video cameras that if there's line of sight to the ground, you can transmit that information down in more or less real time. And there's new sensors going up on the ISS, high definition external cameras that will, that's the intent. The intent is to actually have it in real time so you can view exactly what is being seen from the space station, from the ground.
That's excellent. Do we have any more questions? I think we have just a little bit of more time.
Let's say a ship passes over the seafloor that has a reverse magnetic polarization. How would this affect the magnetic field reading?
For that question, and a great question, the ship's compass wouldn't see any effect. It would just see the regular, the current Earth's magnetic field, and that's mainly because the ship is so far away. It's far enough above the seafloor so that you won't get any effect from remnant magnetization. The way that was originally discovered was by towing sensitive sensors behind ships, so they were pretty much right over the seafloor. And when you do that, you can see the difference in the magnetic field orientation from the minerals that were frozen into the seafloor when it crystallized. But from a ship on the surface, no, you wouldn't see any effect from it.
If you see dangerous weather coming to a certain area, who do you usually contact?
Okay, I think you mean, are you asking if you see dangerous weather from orbit or on the ground?
Yeah. On the ground.
Okay, well, if you see dangerous weather coming on the ground, like a tornado or something like that, well, the first thing I would do is attend to your own safety. First, find somewhere that's out of the path, but then you would consider calling your parents or the local police department, fire department. Typically, though, for most of these, this is an advantage of the weather satellites. For a lot of the big storm systems, even for tornadoes, we're improving our ability to be able to detect where those might occur from orbit. So we're trying to improve the ability to warn people in the path of, say, tornadoes that keep on the lookout, something might be forming.
Thank you. How accurate can you measure the speed of the continents moving?
Well, we have a lot of fans of plate tectonics in the audience today. With GPS satellite measurements, you can actually measure the speed of the continents down to millimeters per year. But typically, geologists, we tend to measure the rate in centimeters per year. And on average, the continents are moving between about 2 and 10 centimeters per year. And that's about the same rate your fingernails grow.
Do we have any others? This is really exciting. I'm enjoying these questions and answers here.
Can you tell us a little bit about your research?
Oh, didn't know I was going to talk about myself here. I'm a geologist, and most of my research is done using data from satellites to look at the Earth's surface. And in particular, I do a lot of work in mapping where different minerals are, different rocks and minerals, so geological mapping. Also, I do a lot of work in human-dominated systems. Like I look at urban heat islands where cities get hotter than their surrounding environments, and in particular where people in those cities are most at risk from high heat events. So my thing is basically like geologic hazards in general, but particularly looking at geologic hazards around cities. So that's what I spend most of my time doing.
That's where those good geology questions were really great for us today.
Exactly.
Earth rocks.
Thank you.
Do we have any others?
Does anyone else have a question? Okay. What? Oh. If satellites have a
Okay, I think that's all the time we have. Guys, we really, really appreciate those questions. They're really great questions. Thank you again, Will, for coming out and talking with the students. I hope you all
You're very welcome.
learned something new. I know I did. Go back to working there and studying hard and making your way to where you want to go. Thank you very much for coming.